At the Norinaga Laboratory, School of Engineering, Nagoya University, we are developing simulation technologies to support reactor design for the thermochemical conversion of carbon resources such as coal and biomass, and for processes that produce synthetic methane and liquid fuels through the hydrogenation of carbon dioxide, including methanation over solid catalysts. A key feature of our work is that we aim to comprehensively understand chemical reaction rates, the heat absorption and heat release associated with chemical reactions, and fluid flow. We seek to seamlessly model phenomena ranging from microscopic chemical reactions to macroscopic fluid flow, and to reproduce the behavior of fluids inside chemical reactors on a computer. Our laboratory is equipped with experimental systems for understanding the essential nature of chemical reactions. This is a test apparatus equipped with a quartz spiral tube for investigating gas phase reactions under high-temperature conditions. Using mixed gases that simulate gases generated from coal and waste materials, this apparatus can track reaction characteristics at temperatures of up to 1,200 degrees Celsius, while varying the residence time. This is a biomass pyrolysis test apparatus. A small amount of biomass is used as the sample and is dropped into a preheated heating section, enabling rapid heating. This reactor is directly connected to a gas chromatograph, making it possible to analyze the composition of gases generated through pyrolysis. By changing the volume of the downstream section of the reaction tube, it is possible to track the gas phase reaction characteristics of gases generated by pyrolysis. The data obtained in this way are compared with the results of reaction simulations using chemical kinetic models developed from elementary reaction databases, extending down to the level of molecules and radicals. This is a methodology that our laboratory has cultivated over many years. The results are then used to improve the accuracy of the reaction kinetic models. The reaction kinetic models constructed in this way are coupled with models of flow, including turbulence inside the reactor and heat transfer. This has led to the visualization of fluid behavior inside reactors for hydrogen production through gas phase partial oxidation of coal carbonization gas, with the aim of applying these models to reactor design at demonstration and commercial scales. The measurement of chemical reaction rates over solid catalysts is carried out using a small fixed-bed reactor packed with powdered catalyst. In our laboratory, we use this apparatus mainly for methanation. We comprehensively measure reaction rates under gas composition and temperature conditions expected during the process in which carbon dioxide and hydrogen, the feed gases for methanation, are completely converted into methane and water. Because the methanation reaction is exothermic, the catalyst is diluted with inert particles as necessary in order to suppress the extent of reaction and promote heat dissipation, thereby ensuring isothermal conditions. This allows the reactor to satisfy the requirements of a differential reactor, in which the reaction temperature and gas partial pressures can be clearly defined. The flow rates and compositions of the feed gases are controlled by mass flow controllers. The gases pass through a preheater and are then supplied from the top of the reactor, where the reaction proceeds over the catalyst. The composition and concentration of the product gas after reaction are measured online using a gas chromatograph or an infrared gas analyzer. A key feature of this apparatus is that measurements under various conditions can be automated by pre-programming a sequence of operations, including the flow rates and temperatures of each feed gas, as well as sampling of the outlet gas and its introduction into the gas chromatograph. By comparing the reaction rate data obtained in this way with calculation results from the reaction kinetic model, parameters included in the model, such as frequency factors and activation energies, are determined. To verify the validity of the resulting reaction kinetic model, comparison with experimental results obtained under conditions that simulate actual operation is essential. This is a high-pressure integral reactor, which can be operated at pressures of up to 3 megapascals. We have two types of reactors: one with temperature control using an electric heater, and another isothermal type, in which thermal oil is circulated through a jacket. A multi-point thermocouple is inserted along the central axis of the catalyst bed, enabling measurement of the temperature distribution within the catalyst layer. Using the reaction model constructed based on the results from the differential reactor tests, we couple the reaction model with a one-dimensional plug-flow reactor model that can account for the reaction and the axial temperature distribution inside the reactor. This enables simulation of the temperature distribution and the concentration distribution of each gas inside the reactor. By comparing the outlet gas composition obtained experimentally with the simulation results, we verify the validity of the reaction mechanism. In addition, we correct the reaction rates obtained from the differential reactor using powdered catalyst so that they are consistent with the behavior of an integral reactor using catalyst particles of several millimeters, which are used in practical operation. Through this process, we refine the model into a reaction model capable of reproducing the behavior of an actual reactor. The final stage of the simulation process begins here. The reaction kinetic model obtained in this way is combined with three-dimensional thermal fluid analysis, allowing us to visualize distributions of temperature, concentration, and flow velocity inside the reactor. At Nagoya University, we are independently developing reactor thermal flow simulation technology that couples reaction kinetic models with flow and heat transfer models, using an open-source platform rather than relying on commercial software. After verifying the validity of the model through comparison with laboratory-scale isothermal reactors, we are advancing its application to demonstration-scale and commercial-scale reactors. Through this analysis, it becomes possible to quantitatively identify in advance issues that may become apparent during scale-up, such as temperature distributions inside the reactor, heat removal characteristics, and uneven flow distribution. Our goal is to obtain insights that contribute to risk reduction at the design stage and to the study of optimal reactor structures. Through chemical engineering, we are committed to contributing to the development of technologies that society needs in order to achieve carbon neutrality.